In this page, we are going to talk about vapor pressure depressions. And so vapor pressure is part of Raoult's law. So Raoult's law states that the vapor pressure will depress depending on what kind of stuff you have in it. Okay, and so it's about solutions. Okay, and so let's look at the first problem here. Vapor pressure of benzene at 25.0 degrees Celsius is 95.1 millimeters of mercury. What is the vapor pressure of benzene above a solution that is 5.05 grams of benzoic acid? And the formula is given, mass is given, dissolved in 245 grams of benzene. Okay, so that's the problem given to us. A lot of data is given to us also. So let's look at the formula first, okay, for vapor pressure. So vapor pressure of the solution is going to be the mole fraction of the solvent, which here in this case is benzene, times the vapor pressure also of benzene. Okay, now I'm maybe writing benz, but remember that's not going to be benzoic acid, that will be benzene. Okay, so which means that I need to really calculate the mole fraction over here, all right, for benzene. So then what I have to do is I have the grams of my benzoic acid and I have grams of benzene, the solvent. So I need to find the mole fraction of benzene, okay, over here. So let's go ahead and get started. And we have first to calculate the moles of benzoic acid. You can do whichever one first, it doesn't really matter. Okay, so 5.05 grams of benzoic acid, that's Ba, times 1 mole over 122.1 gram, which is 0.0414 moles. Yes, you can see it's so exciting. Moles of benzene, which, you know, we've done this a zillion times. 245 grams of benzene times 1 mole divided by 78.1 grams, and this gives us 3.14 moles. Okay, so to find the mole fraction of benzene, then we will have to take 3.14 divided by 3.14 plus 0.0414, 0.0414. Yep. Okay, all right. Once we have that, we have the mole fraction, which is 0.987. That's the mole fraction of benzene. So then the vapor pressure of solution is going to be 0.987 times 95.1 millimeters of mercury. That is then 93.9 milliliters of mercury. And that's what the Raoult's law states also. That's what we learned in before also with solutes, okay, is that if you have a solute dissolved in any kind of solvent, it will depress its vapor pressure. Okay, and so that's what we see over here. The original was 95.1 and the final is 93.9 because the vapor, the mole fraction coming from the solvent now is much less. Okay, so let's do one more. And here now in the second one, vapor pressure of pure water at 20 degrees Celsius is 17.5 millimeters of Hg. What is the vapor pressure of water at 20 degrees Celsius above a solution that is 0.25 molar sucrose and 75 grams of urea? So here we actually have two solutes, okay, and we have 1 kilogram of water. All right, so in this case we need to make sure that we add the 2 moles together, okay, for urea and the sucrose. All right, so let's go ahead and again we need to find out the vapor pressure, right? So you know how to get started from before there. So first of all, the mole fraction of the solution is going to be the mole fraction of water times the vapor pressure of water. Okay, so we're looking for mole fraction of water. So then we have moles of sucrose already given to us, which is 0.25 moles, and moles of urea is going to be 75.0 grams times 1 over 60.06 grams, and that moles is equal to 1.25 moles of urea And then we have to find the moles of water, which is 1 kilogram of water, that's given over here. So then 1000 grams water, 1 mole water has 18 grams. This is 155.5 moles of water. Alright, so then total moles of solute is equal to 0.25 plus 1.25, and this is equal to 1.50 moles then. So then the mole fraction of water is equal to 55.5 moles divided by 55.5 plus 1.50, and this is equal to 0.974, and you can see that the number of moles of water has decreased. So then sorry, this should be BP. Alright, so then the vapor pressure of the solution is going to be 0.974 times 17.5 millimeters of mercury, and that is then 17.0 millimeters of mercury. So you can see that yes, even in this small amount of solute we were able to lower the vapor pressure of water.